All right, let's look at another example here. All right, suppose that you were to take out a $100,000 15-year mortgage at a monthly interest rate of 0.25%, which turns into an annual rate of around 3%, which is about where the rates are at the moment. And suppose that each month the bank requires that you make a monthly payment of $690.59. Let's try to compute the balance of the loan after 5, 10, and 15 years, and we'll use a difference equation to help us do that. All right, to start, let's try to set up the model. So we need to be able to relate all this information in the problem to the general form of a difference equation, which, as you recall, is the new value of the state is equal to the old value plus the change. All right. So notice we're told that initially we have a $100,000 mortgage. So A0 must be 100,000. And we have a monthly interest rate here. So that means that each step should probably represent 1 month. Now, you could also find a way to convert this into a yearly mortgage, but we're going to ignore that for now, and we're going to focus on months. All right, so A1 is going to be 1 month. That means A12 would be 1 year. And so if we want 5 years, that's really going to be the value of A at 5 years. 5 times 12 would be a 60. We want 10 years, so that would be A120, and A15 would be, 15 years would be 180. So that's what we want to find. And we need to then find a formula that allows us to compute future balances of this mortgage based on the current balance. Okay, and so we'll write down our update rule. AN plus 1 is equal to AN plus delta A. But delta A, what is the change in A? Well, the balance changes for 2 reasons. One, there is interest, right? You have to, because you have lent the bank or the bank has lent you money, you have to pay a little bit of extra. The balance is going to grow as a result of the interest. And so we could write that down. 0.25% would be, 0.0025. And that's the interest rate, and so that needs to be proportional to the balance. So every month, our balance is going to increase by 0.0025 times the current balance. And then we're also making a payment, which means we are going to decrease the balance by a fixed amount, and our payments were $690.59. And so every month we have 2 factors. We have the increase due to the interest and the decrease due to the payments. And so our model is going to look like AN plus 0.0025 AN minus 690.59. And that one is not proportional to AN because we pay the same dollar amount regardless of whether we owe $100,000 or $1,000. Okay? And we could simplify that model just a little bit. We could group the AN terms together, and that would give us 1.0025 AN minus 690.59. Okay? All right, so there we go. We have our model set up. Now I'm going to skip ahead a couple of slides, and we'll look at how we could then use the computer to analyze this. All right, so here I've written down some of the key information from what we just showed before, but instead of actually plugging in the interest rate and the payments, I've just left them with names. So we have R and B in place of the interest rate and the monthly payments respectively. And if we want to write down a program, you might want to leave those as variables so that you can easily change your program to simulate a different interest rate without having to find down every place that you wrote 0.0025, or similarly, you could change your payments without having to track down everywhere you wrote $690. And so you could create variables R equals 0.0025 at the beginning of your program, and B equals 690 whatever we said, I think 0.59. And then that way you can just use R and B in place of the numbers for the rest of your program. All right, we talked about how to set up a difference equation in MATLAB before, so I won't go through this quite as carefully, but we do need to know how many months we need to simulate for, and so in this case, we should simulate for a total. We said we need to compute the balance after 15 years, which is a total of 15 times 12, or 180 months. And so that's how many times we're going to have to cycle through our loop, 180. All right, so as before, we will need to define the initial value for the state. And so that's what this first line does. A of 1 is 100,000. And then we'll use our loop to compute A2, A3, A4, and so on. And in this case, rather than writing a function down for the update rule, I actually just explicitly put in 1 plus r times the current value minus b. And it will apply that. So the first time it computes A2 using A1, the second time it computes A3 using A2, and so on. All right, so that is the code that would be needed to actually compute the values of A at every point in time. And then if we want to actually get our answers, all we need to be able to do is extract that information from the results. And so remember, we had this issue with the indexing where A1 in octave corresponds to A0 in what we were writing on paper. And so if we want month 60, we actually need to use A parentheses 61. The index is going to be off by 1. And this suggests that after 5 years, we will have a balance of $71,000. So you owed $100,000 initially. You've been paying it for 5 years, which is a third of the total term for the loan, and you've paid off, well, less than a third of the loan. And that's because at the beginning you're mostly paying off interest. And then 5 years later, you're now going to be at $38,000. So there again, we've paid off a little less than a third, but we made a little more ground over the next 5 years because you owe less, and so your interest is less. And then in the last 5 years, we pay off the remainder, and I guess your last payment would probably be $1.90 lower, so the bank doesn't owe you money at the end. But if it's a 15-year loan, the bank usually calculates the payments so that your last payment pays off down to the last cent exactly what you need. Okay, so numerical solutions can allow us to determine the balance at any point in time. Those were the 3 that we're interested in. But let's take a minute to think about how we could do this without the computer. Now, this is something that's a little bit more involved mathematically, and I don't know that I'll put a lot of problems like this on the homework, but it is helpful to understand how you can do analytical solutions for models that, like this one, that are a little bit more complicated than our previous one. So let's go back to our formula again. All right, so our model was an plus 1 equals 1 plus r times an minus b. So let's write down what the first couple of terms would look like. We'll just have a0, and then a1 would be equal to 1 plus r a0 minus b, and a2 would be equal to 1 plus r times a1 minus b. But notice we already have a formula for a1, so we can plug that in. And so that would be 1 plus r times, plugging in a1, we have 1 plus r a0 minus b, and then we have a minus b on the end. And if we multiply that out, we'll have 1 plus r squared times a0 minus b times, notice we'll have a b with a factor of 1 from right there, plus we'll have a b with a factor of 1 plus r from right there. Okay, so that's after 2 months. And let's continue on, see if we can find the pattern. A3 is going to be 1 plus r times a2 minus b. And again, we have a formula for a2, so let's plug that in. That is 1 plus r times everything that's above, 1 plus r squared a0 minus b times 1 plus 1 plus r, and then we have minus a b. And again, like the previous one, I'm going to group together the terms with a0s and the terms that don't have a0s, and so we'll have it looks like a0 has an extra factor of 1 plus r now, so it's 1 plus r cubed. And then if we look at the b terms, notice I'm going to have a term that's just a b, so b times 1. And then I'm going to have a b with 1 times 1 plus r, so there's a 1 plus r. And then I'm also going to have a b times 1 plus r times another 1 plus r, so 1 plus r squared. All right, and at this point you may start to see a pattern, so let's make a conjecture. An equals, notice the power that was in front of a0, we had 1 plus r raised to the 3 when we were on a3. It was 1 plus r to the 2 when we had a2. And so it seems like we have 1 plus r raised to the n in each case, multiplied by a0. And then b is multiplied by, well, notice we have 1 plus r squared, and then this 1. It seems like we're getting all the powers of 1 plus r up to 3. And so we can write this as the following. The sum from k equals 0 to n minus 1 of 1 plus r raised to the k. And notice when k is equal to 0, 1 plus r to the 0 is just 1. And so the k equals 0 is right there. When k equals 1, we get the next term, 1 plus r raised to the 1. And then when k equals 2, we get 1 plus r squared. And it seems like that should account for all of those factors of b. Okay? So that is a conjecture. We would then potentially want to prove this. So let me try that again. So we had our conjecture is an is equal to 1 plus r raised to the n times a0 minus the sum of k equals 0 to n minus 1 of 1 minus r plus r raised to the k all times b. And so let's see if we can prove that that works. We'll first need to prove the base case. In other words, does this formula work for some particular value, the first value? And so let's compute a0 according to this formula. It's going to be 1 plus r to the 0 times a0 minus, notice here, when we look at that sum, if I plug in n equals 0, the upper limit is lower than the lower one, right? We start with k equals 0, and it says we end with k equals minus 1. So there's really nothing to add there. And so minus 0. And notice, therefore, we get 1 plus r to the 0. That's just 1. So we get a0. So for the base case, that formula gives us the right answer. And then we need to look at the inductive case. So we're going to assume that the formula works. And then we need to show that it works for an plus 1. All right, so let's try that. We'll first use our update rule. An plus 1 is equal to 1 plus r times an minus b. And if we plug in our assumption for an, we plug that in, we will have 1 plus r times 1 plus r to the n a0 minus b times the sum. And then minus a b. And if we simplify that down, notice in the first term, we're going to have a 1 plus r, a total of n plus 1 times. So that checks out. And then if you look at the second term, notice we're going to have a b times 1 from over on the right. And then we're going to have b raised to a whole bunch of other powers, 1 plus r raised to the 1, 1 plus r raised to the 2, 1 plus r raised to the 3, when you combine those two terms. And so if you put that all together, you'll get the sum from k equals 0 now up to n of 1 plus r to the k, which is exactly what this formula up here would have been if we replaced all of the n's with n plus 1. Okay, so we've checked the base case, we've checked the inductive case, and at that point we have proven that this formula is indeed correct. All right, so we will stop here and look at some more interesting examples that don't come from banking next time.